Dr. Ajit, you cannot able to listen us.
No, I am not able to hear you.
Professor Ajit, can you able to listen us? Can you able to listen us?
Because I think he cannot hear us.
Hello. 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 Okay. Presentation. Presentation. Okay. Okay. ठीक है.
Cancel it and click on again.
So participants, I welcome all of you to the third day of the advanced optimization technique with MATLAB online FDP. Here we have with us today Dr. Ajit Kumar Sahu. He is an associate professor at Department of Electronics and Communication Engineering, National Institute of Technology,
Is it
Rourkela.
visible all of you? My screen is visible to all of you?
Yes, it is visible. And your voice is also perfect. So you can make it full screen.
My screen is visible to all of you?
You can make it full screen. Yes. So you can go ahead with the presentation, Professor Ajit.
My screen is visible.
Yes, sir, it is visible.
Hello. Just tell me, my PPT is visible. Okay, then I'm going for continuing. Okay. Good afternoon to all of you. So my presentation will be on alternative directional method of multipliers for optimization, introduction, convex optimization techniques, alternative alternative direction method of multipliers, then we'll go for one application. So an optimization algorithm is a procedure which is executed iteratively by comparing various solutions till an optimum or a satisfactory solution is found. So nowadays, almost all optimization algorithms are not in the closed format. We have to go for, we have to put it iteratively to find out the final solution. And in this particular presentation, I will go for only convex optimization, which is a special class of mathematical optimization problems, which includes least squares and linear programming problems. The most basic advantage of convex optimization is that the problem can be solved very reliably and efficiently. So what is a constant optimization? So every day the problem which are solved almost all in the on constant format. That means if I'll say that minimize x square plus y square, so that is on constant. We are not putting any constant on x and y. But in mathematical optimization, constant optimization is the process of optimizing an objective function with respect to some variable in presence of constants on those variables. So now, without going for when I write down minimize fxy with x minus 1 whole square plus y, only this one, that means this is on constant optimization. So finding out on constant optimization solution is very easy. Just take the differentiate and get the point of inflection and then go for the second derivative to find out minimize or maximize. But whenever it is a constant one, then according to this constant, we have to find out the solution. So in mathematical optimization, so mathematical optimization or optimization problem has the form minimize f0x subject to fix less than equals to 0, hix less than equals to 0. So this is minimize, this is called objective function, and these two are called constants. So we have to find out the minimum value with the presence of these constants. So this x is have multiple number of variables. So these are called optimization variables, and f0 is called cost or objective function, which is from Rn to R. So that is a function, and fi. So these functions, this is called inequality constant, and this is called equality constant. So this fi is from Rn to R are inequality constants, and hi, these are called equality constant. So minimizing a function in the presence of these constants are challenging as compared to without constant. So whenever we'll put some constant, we have to check it that your optimal solution should obey these constants first. Then out of those many optimal sets, out of that optimal set, we have to find out one solution which is minimize this f0x. So the optimal set will get from these constants. From this constant, we will get the optimal set. After getting the optimal set, so we have to choose the optimal solution. So now solving the optimization problem. So this is the optimization problem format. Okay, many of the optimization problems you can put in this format. Then solving the optimization problems. So your general optimization problem is very difficult to solve. Methods involve some compromise, long computation time, or not always finding the solution. So whenever you take any arbitrary optimization problem, it is very difficult to solve. But there are some exceptions. Certain problems classes can be solved efficiently and reliably. For example, least square problems, linear programming problems, convex optimization problem. So these class of problems, you can solve them easily because many softwares are available, many type of already established algorithms are available for these three type of problems. So least square problems has the form minimize ax minus b, that is the norm to square. So least square problem is an unconstant problem. So there is no constant. So this is a very popular problem. Many people are using today. Whatever the solution you are getting, like MSE, mean square error problem, or your data fitting problem, all other belongs to this type of problem. So here the constants, there is no constant. The solution of least square problem can be used to. So how to get the solution? because it is a minimized problem, so just take the derivative of that and equate to 0 and get the solution. So if you take the derivative, you will, and finally you get this is the solution. So this is a, if we are able to identify the problem is a least square problem, just go for this is a closed form solution. So if you can represent like this way, you will get a closed form solution like this way. So reliable and efficient algorithm and software, it is a mature technology. Least square problems are very easy to recognize. So the least square problems are very easy to recognize. You only have to say the problem is in this format. Then next one is a linear programming problem. So the linear programming problem in this format. So minimize C transpose X such that AI transpose X is less than equals to BI. So this is in this format. So you see here the function as well as the constants, these are the linear functions. So solving the linear programs, no analytical formula or solution. So like earlier in case of linear, the analytical formula is available, but in case of a linear programming problem, there is no analytical formula is available, but reliable and efficient algorithms and softwares are available. For example, if you go to any software like MATLAB or Python, for the linear programming problem, there is a library is available. So you can use them and you can find out the solution. And this is a mature technology. So to recognize the problem as a linear problem, so just you have to see in this format. The third one is convex optimization problem. So it is of the form minimize f0x, fi(x) less than equals to 0, and aix is equal to bi. So this is the convex optimization problem is in this format. In convex optimization problem, objective and all the constant functions are convex. So we'll see what is the meaning of convex. But remember, whenever this is in this format, just that is called convex optimization problem. But each function has to obey this condition, that is fi alpha x plus beta y is less than equals to alpha fi x plus beta fi y if alpha plus beta is equal to 1 and alpha is greater than equals to 0, beta is greater than equals to 0. So this is called convex optimization problem. So this is equality constraint. You see the equality constraint affine. In case of convex optimization problem, the equality constraints are affine, and it includes least square problem and linear programming problem as a special case. For example, if you remove these two, now it will become this one. This is a least square problem, and if this fi(x) is a linear function, then that becomes linear programming problem. So convex optimization problem includes also least square problem and linear programming problem. So if you see these three type of problem, if you are able to find out, then you can easily solve it. So for least square problem, by seeing that problem, you can say that this is least square. It is of the format this one. Like up to today, many solutions you are getting minimizing the mean square error. So all are belongs to least square problem, like LMS algorithm, RLS algorithm, type of algorithms are least square problem. And linear programming problem. So many linear programming problem you may have like your data fitting. So you can do, and so but the linear programming problem, it should be in this format only. And when we go for the convex optimization problem, so you have to say the function should obey this condition. Then only the, so if you are able to find out the problem is convex problem, then there are also softwares available like in MATLAB and Python for convex, like CVX function is available where you can find out the solution. Only thing that you have to find out which are the problem is convex. So now solving the convex optimization problem, no analytical solution. Like least square has analytical solution, here no analytical solution. Reliable and efficient algorithm. So here you will get reliable and efficient algorithms are available. Often difficult to recognize. Only thing the problem is you have to recognize the problem is convex or not. That is the thing you have to recognize. Many tricks are available for transferring the problem into convex form. If you are able to analyze or you are able to transform the problem to the convex form, then you can solve it. Surprise, many problems can be solved via convex optimization. So let's go to understand the convex problems. Now, for that, let's see what is an affine set. So an affine set of the form. So affine set means, suppose this is a set. Now you take 2 points and join it, go from minus infinity to infinity. If it remain inside that, then that is called affine set. So this, the drawing what I have drawn here, this is not an affine set because I have joining the line. So if it is going from minus infinity to plus infinity, it is not remaining inside that. So this is not an affine set. So the affine set, the mathematical formula is like this way: x is, that is all the points like x, theta x1 plus 1 minus theta x2, theta belongs to R. So if theta is 0, then this point to x2. If theta is 0, this is x2. If theta is 1, so this is x1. So you can choose many theta, like if theta is 1.2, it will go this side. If theta is increasing, it will go this side. And theta is decreasing, it will go this side. So this is called affine set. So affine set contains the line through any two points in the set. The solution set of linear equation, this is an affine set. The solution set of linear set is an affine set. Conversely, every affine set expressed as solution set of system of linear equations. So this is affine set. Then come to convex. The convex set means you take any set like this way and take 2 points and join it. If you join it, and if the lines lies inside the set, that is called convex sets. So here this one is a convex set, this one is a convex set, and this is not a convex set, this is a convex set, because if you choose any 2 points, so like if you choose this point and this point, if you choose, then it is not inside that set. If you join it, so it is not inside that, so it is not convex set. So what is the difference between convex set and affine set? Here it is, the line should be inside the set. That means the theta belongs to R, then that will be line. This is theta belongs to R, but this is constant. The theta must be in between 0 to 1. Then that is becomes line segment. If you draw this equation, it will come from one point to another point, only line segment. So that is called convex set. Then come to convex function. So the convex function means, if you take this type of function, now you take 2 arbitrary points and you join it. Okay, this type of function, if you take any 2 arbitrary point, if you join it, if this line lies above this function value, then that is called convex function. So this is the mathematically can be written as like this way: f of theta x plus 1 minus theta y is less than equals to theta of x plus 1 minus theta fy. So this type of function is called the function which obey this relation, that is called convex function. For convex function, remember this domain must be a convex set. That means domain means this argument must be a convex set. So that is a convex function. If f is concave, then minus f is convex. So like convex, the another function is called concave. So that means if you take any 2 points, if you join it, the line lies below the function, then that's called concave function. So the convex function, so it is like here, this is f of theta x, this equation, if you see, it is generally, you can see here, so this is the line, this is the function, and this is the f of theta x plus 1 minus theta y, and this is the domain, this is the x, that is the theta x plus 1 theta y. So because it's the starting point, it is the ending point. So if you change the theta within 0 to 1, it will start from here and it will end, and it will remain inside that. So that is the domain. So that is, domain must be a convex set, and your convex function, that means if you take any 2 points, if we will join it, the line should be lies above that. For example, here this is a convex set, convex function. So it is also called strictly convex. Okay, you see, this is also convex. If you join any 2 points, so it is lies above. But if you will take 2 points here and here, so it is lie exactly on that line. So it is called only convex, and this is called strictly convex. Strictly convex means, if this less than equals to, only less than is there, that equality will not be there, then that is called strictly convex. So this is called concave function. You take any 2 points here and join it, it lies below that, that is called concave function. So this is non-convex function because if you here 2 points, it is lies above that. So, but it is not convex because if I choose these 2 points and you join it, it is lies below that function value. So this is non-convex. For convexity, you have to take any points arbitrarily. Then it has to satisfy all the conditions for all the points. So this is about convex set and convex function. Then duality, two different views in the same object. So as you know earlier, if duality, one thing you have seen in the time domain, if you the different things you can the frequency domain, and you know why we are transferring from the time domain to frequency domain, because the solving the analysis will be better in the frequency domain. So, but in this talk we are not going to frequency domain. For example, I have just put here this picture. We'll go to another domain for analysis this problem, analysis of the problem. So the Lagrangian. So next you will see the Lagrangian. You see the standard problem of this one, how to solve the constant optimization problem. So it is of the form f0x, subject f(ix) less than equals to 0, hix is equal to 0. So how to first you form the Lagrangian. So to form the Lagrangian, you have to take the objective function and you have to take the some weighted sum of the fix and weighted sum of the hix. And this lambda I is the Lagrangian multiplier associated with fix less than equal to 0, and nu I are the Lagrangian multiplier hix equal to 0. So now you have to first form the Lagrangian. Then after forming the Lagrangian, then you have to find out, you have to minimize this one. The Lagrangian you have to minimize with respect to x. The Lagrangian has to be minimized with respect to x. If you minimize with respect to, so this minimum is nothing but the minimum. So if you minimize with respect to x, you will get this type of expression. Then after minimum, so this is it will be function of g of lambda and nu, because you are minimizing with respect to x, then x will not be inside this function after minimizing. So the procedure is same. How to minimize? You take the derivative and find out the inflection point, then put there. So we have to go in the same procedure. So finally you will find out a function like g lambda nu. So when you see this g, it will be a concave function. It will come like this way. It will come a concave function. So now actually the original function is like this way. Minimize f0x. This is a convex function. Okay, the original function is like this way, but you have to minimize this. So you have to get this point. The original function is a convex function, concave function. The original function is like this way. The original function is a convex function this way, but when you are forming the Lagrangian and you will find out the function g, it will come like this way, concave function. Okay, so now you'll get g. If suppose inside your problem this inequality constant will not be there, so the form will come like this way. So only that lambda, this part will not come. This part will not come. Okay, if only equality constant will be there. Why I am telling only equality? Problem which will deal with in this talk is having only equality constant. There is no inequality constant. So what will happen? This is g, the function. This will be the function g. This is the function f0. So now we have to maximize the function g, and we'll get this solution. After getting, we'll get this solution. So after maximizing, you will get the solution here, but the original function will come here. Okay, so if your duality is strong, then these two will be matched. Okay, otherwise this can be used as the lower bound. So that means the original function cannot go below this. You can estimate like that way. So minimizing overall over all point, so you'll get p star. So this is your original function minimize. This is your original function minimize point. Okay, so the original function, the minimum point, always above the duality function. So this is your dual function, g of lambda nu. Okay, so why we are going to dual function? Because if the original function is not also convex, the dual function is always concave. So that means you will get always. You will get this point always. So at least you can estimate that this function cannot go below this point. Okay, if both will match, like the maximum of this dual function and the minimum of this primal function, if both will match, then the solution will be same. So for example, in this case, you see, this is a equality constraint function. So minimize x transpose x, ax is b. Now you form the Lagrangian, you take the nu transpose ax minus b, you form the, because only equality constraint is there. So after forming the Lagrangian, you take derivative with respect to x, then if you get x will be this much. Now you take this x, you put here. If you put here, then it will be a function of nu only. Okay, it will be a function of nu, and you will get this much. And if you draw this one, this nu is a concave function. Nu will get it is a concave function, but your p star, the minimum value, will be somewhere here. Okay, so it is a lower bound property. You can say the p star will be always equal or above than that. Okay, so even if, for example, the primal solution p star, this is it is not convex function. Okay, but the dual function will come always a convex function. So that the maximum value, this maximum value will be below that. Okay, at least you can get this solution easily. So we can strong value, primal optimal value denoted as p star, dual optimal value denoted as d star. So this is your p star, this is your p star, and this is your d star. So this is the dual solution, this is your primal solution. So weak duality always holds. This your d star is always equals to p star, can be used to find non-trivial lower bounds for difficult problems. Sometimes the problem will be so difficult, we have to find out the lower bound for this primal function. So because the problem is so difficult, we cannot able to find, because the problem is non-convex, it is very difficult to find out. So what we'll do, you transfer this problem to the dual domain, which is a concave function, then you find out the maximum of this one. So at least you can say the minimum of this function, primal function, cannot go below this maximum function. So that type of inference you can draw by using duality. Then strong duality does not hold in general, it is too difficult to hold, but it usually holds convex problem. If your primal problem is a convex problem, then you can generally d star is equal to p star. That means this one, this is the primal function, and the dual function, it will match like this way. So exact solution you will get. Conditions that guarantee strong duality in convex problems are called constraint qualifications. So for the strong duality, so the problem has to obey some constraint qualifications. So which I am not going inside this. Okay. So regarding the duality and weak duality, strong duality, convex function, and convex set. So with this background, we'll go for the algorithms. Now come to the first algorithm, that is the dual ascent. So dual ascent, so this problem is of the form minimize fx subject to ax is equal to b with variable x belongs to r to the power n, and these are the dimension of this each of this one. So now the same way we have to first form the Lagrangian. So here yt is your dual variable. So the dual function, if you find out, this is because here only equality constraint, so it will become a function of y only. Then the gy is a concave function. This is always concave. So if this is always concave, irrespective of this fx is convex or concave, that doesn't matter. But in this dual ascent, it assumes that fx is convex. So gy you will get infimum of lxy. Now you find out x from here, and you find out the gy directly here. Then because this is a concave function, that means it will be in this shape. Then you have to find out maximize it. Okay, you find out the maximum of here. So after getting maximum, so function, then you can go for the solution. So assuming that strong duality holds. So strong duality means the primal solution same as the dual solution. So the optimal values of the primal and dual problems are same. Primal optimal point x star can be found from a dual point y star as this. Okay, you see, if you are going for the minimizing this one, then you'll get the this is the optimal value. Okay, so but we'll go for the iteration procedure. So that means the next iteration value xk plus 1 is equal to arg mean. This is the Lagrangian x yk, and yk plus 1 will be yk plus alpha x, alpha to the, this is one step size parameter, ax to the power k plus 1 minus b. So this is the way to get the dual ascent algorithm. So like other algorithms, so this is also one of the algorithm. So here assumption that f is strictly convex. So here this has to be strictly convex. So that is the dual ascent algorithm. Then dual decomposition. So in case of dual ascent, so the major benefit is this one. If the function is a summation of many variables, or the function can be decomposed into a number of functions, then you can partition the problem into n number of problems, and those n number of problems you can solve parallelly. So that is called dual decomposition. Like the Lagrangian, it can be formed like this way. So each Lagrangian can be summation of the total Lagrangian can be summation of each Lagrangian, and you can have n number of this type of functions. Then you can solve them parallelly. So the x minimization step is carried out independently in parallel. So you can see here this step you can minimize them parallelly for each with respect to dual ascent. So this can be used, this algorithm can be used for distributed optimization because it can be solved parallelly by using a number of computers or number of nodes, you can say. So if you are able to decompose the optimization function like this way, then you can solve them parallelly. Then come to augmented Lagrangian method and method of multipliers. So what happens in this case? In this case, what happens? It needs the function to be strictly convex. Otherwise, you will not get the solution properly. So here, what will happen? The same thing will be there, but we'll add a strict convex term here. You see, whenever it will obey the constant ax is equal to b. So you see the constant here, ax is equal to b. If you'll get the solution x, that means other solution ax will be equals to b. If ax is equal to b, then this term will go to 0. It will not hamper the solution. If ax, but what will help? Adding this term, it will help you. Convergence will be faster. So the modifier problem. So like that way, you can have the stepwise iteration method. That is xk plus 1 is equal to argmin LO xyk, and similar same type of solution you'll get. Only thing that you are the Lagrangian will be added to another term. So adding this term will not the solution, because when the constant will be satisfied at that time the term will go to 0. So it will not hamper the solution. So this is known as method of multipliers. Then we'll go for alternative directional method of multipliers. So you see, in case of method of multiplier, what problems? Because these two terms are here, so now it cannot go for decomposition. Like earlier case, the dual ascent method, if it can go for the decomposition, but this augmented Lagrangian method, because these two are coupled here, so now you cannot separate them. So they cannot go for the decomposition. That is the problem with method of multipliers, or it is called augmented Lagrangian method. So then then we have to develop something which you can go for the decomposition. So that is called alternative directional method of multipliers. So in this method, the function here will be of the form fx plus gz. That means ADMM is an algorithm is intended to blend the decomposability of dual ascent with the superior convergence property of the method of multipliers. So here it is of the form fx plus gz and ax plus bz is equal to c. And here both fx and g are convex. That means earlier which is fx, now they can be separated into two functions. That is fx, here it will be separable to fx plus gz. And there will be one constant like this. That means this fx and gz, they will be related by this way. So where with f and g are convex. So this is called the problem is like this way. Then you have to find out optimal value. So optimal value is nothing but p star is equal to infimum, that is the minimum over fx plus gz, such that ax plus bz is equal to c. So this is the same problem in a different way only written. So now, like earlier case, we have to update x, y earlier case. Now it has to update x, z, and y. So if you go for the updatation, then you'll get this type of, okay, these algorithms are not here, but you can go through any research paper or book, you can get these steps easily. So argument, this is the Lagrangian, then this is also Lagrangian, then you have to, this is the dual variable. So this is called ADMM, that is the alternating direction method of multiplier. So that means you can say this x and z. So two variables are there. So without going for at a time updatation x and z, so what we are going for alternatively. First we have to update x, then you have to go for z. Then after that we will go for the dual variable updatation. So due to this, what happens? This is called alternation because x and z, they are alternatingly we are optimizing. So that's why the name alternative direction. So this helps you go for the distributed optimization technique because of this decomposition. So xk plus 1. So the same method, same algorithm is in another form, mostly used in the research papers, this form only. The same thing, if you will go for this replacement, u is equal to 1 by rho y, then you can reach to this type of form. Okay, both are same, only the algorithm, only the forms are different. Okay, both are the same thing. Okay, though this is called, this is about the algorithm, ADMM algorithm. Now let's go for the application to image restoration. So for the image restoration, for this presentation, we'll go for, this can be applied to any type of image restoration, but only the imaging part we'll see here. Noise in an unwanted phenomenon in the digital images. Possible sources of noise include then various sensors and circuit of digital equipments, signal quantization and communication channels. So these are the various sources of noise. It can be appeared in different form distributions such as Gaussian, speckle, and impulse. Denoising is therefore essential processing technique prior to image segmentation and recognition. So any type of image restoration is an ill-posed inverse problem and can be given as like this way. So this is the observed image G, which this is the original image F, and this is the type. This is the G time is called multiplicative noise vector, and this is additive noise vector. So any type of noise modeling you can represent like this way. So at a time both additive or multiplicative you may not take. You can take either multiplicative or additive. Okay, so if g time is equal to 1, so it will be g is equal to f plus zeta. So this is the additive model. So for instance, Gaussian noise is usually considered to be an additive component, and the additive model is most appropriate when the noise, that model is independent of him. So remember, so additive noise is independent of this original image. Similarly, another type of noise is called multiplicative noise. So an example is called speckle, and this speckle is called model dependent on f. So this is called signal dependent noise. So the multiplicative model is most appropriate when the noise model dependent on f. So multiplicative noise model depends upon the signal itself. So inverse optimization problem, inverse problem as optimization task. So estimation of unknown image f given its measured version g uses the posterior conditionality p f by g in order to infer the f. Maximum a posteriori estimation chooses the f for which p f by g is maximum. So now maximum a posteriori probability is, so arg max p f by g. So according to the Bayes theorem, p f by g can be represented as like this way. Because pg is independent of f, because you are going for maximizing with respect to f, so you can remove this term. It will be pg by f, pf, and this maximizing problem you can convert to the minimizing problem by putting a negative sign and log of, because logarithmic is an incremental, or it's a that means this is a function like this way. So if it is x is increasing, the function value is increasing. So you can put minus log. Okay, the solution to this line and this line both are same. So this is called log likelihood function. So arg mean LGF plus eta. So here this minus log p g by f is called forward model, or it is called data fiddle term, and 1 by minus 1 by lambda log pf is called prior model or regularization term. So here by decomposing this way, you'll get one. This is called data fiddle term, and this is called your prior term. So log pf is called prior term. So forward and prior terms, forward model, how the observation is related with, so with the unknown. It includes deterministic properties of imaging systems such as geometry and sensitivity, and probabilistic properties such as noise amplitude. So this is then is the prior model. Framework incorporate available information about likely behavior of the image to be restored. What we know about likely properties of the solution even before any measurements. So prior means, so you have some prior knowledge about the model, so you have to insert those things. Forward model, how the observation is related to unknown. So here in this case, so this is your forward model LGF, that is minus log P, and this is the prior, or this is called regularizer. So now how to apply ADMM to that one. So you see, it is of the, if you see, it is of the form LGF plus lambda into eta f. So now what to do? So arg mean LGF so that f is equal to t. Now you see this problem in terms of ADMM. Okay, like earlier what I explained for ADM, now it is coming in that form. So now the solution is same as the way the solution you have derived from the ADMM. So first you have to form the Lagrangian, so like this way. Then you have to go for the obturaction. Okay, F obturaction, T obturaction, and you see dual obturaction. So 3 obturations like earlier case you have to do. Okay, so for the speckle, so how to calculate LGF? For the LGF is minus log P G by F. So for the speckle, so this is the Rayleigh speckle, Rayleigh speckle equation. So now from here you find out LGF. So equation 5 involves logarithmic term which is strictly concave. If you see, the logarithmic function has the curve like this. So this is a concave function. So take the transformation y is equal to log fi, which leads to like this way. So now it becomes a convex after taking the transformation. So now the map estimation chooses y for which maximum probability is obtained. So y map estimation is arg mean y lgy plus eta y. So the non-separable optimization problem undergoes variable splitting. So it will go LGY plus eta t so that y is equal to t. So the same thing, the ADMM approach, you will go for the ADMM approach and you will get the 3 things obturatation. So, and at last you have to do again this one, because in between that we have taken one transformation y is equal to log fi. To get the fi, you have to take the fi is equal to e to the power y. So because one transformation you have taken, so finally you have to reverse that transformation to get the final result. So this is the ADMM approach. So this approach we have used for synthetic aperture that are image despeckling. So because the SAR images are very prone to the speckle noise, so we can use this method for the SAR image despeckling. So synthetic aperture radar is an imaging radar where the electromagnetic waves are sequentially transmitted and the scattered echoes are collected by the radar antenna. In case of the SAR, the conjugative time of transmission or reception translate into different position due to the platform movement. An appropriate coherent combination of the received signal allows construction of virtual aperture that is much longer than the physical antenna length. So the basic attribute of SAR is the origin of its synthetic aperture, giving the property of being imaging radar. So this is the basics of the SAR. So in the basics of SAR, so this is a multiplicative noise. If it is a multiplicative noise, so your G is equal to F into G time. So G is equal to your F into your this is will be into, and it will be your G time. So this is the multiplicative noise. So how to take the logarithmic of both sides? So it will become some additive format. So now the new optimization problem corresponding to additive domain, and you have to go for LZX plus lambda into eta x. So now, because earlier it is given G, you have to find out what is F. Given G, this is the measurement, you have to find out what is F. Because when you are transforming, here it is became now given Z, now you find out X. So here you know the P G by F. Oh, that's okay. But here from the P G by F, how to get P Z by X? Because you have changed the model from multiplicative to additive. Now you have to also find out corresponding distribution function to apply the map function. So P Z by X, you will get P G by F into, okay, this is one formula is available in this reference to get P Z by X. So if you do this one, so you will get this simplification, and you will get minus log P by Z. So this way, if you take all the simplifications, you will get all these terms. Okay, so this is about the forward model, and for the prior model, so here the prior is taken from the regularization by, this is the regularizer, that is the regularization by denoising. This is one of the interesting paper. You can see, just put this regularization by denoising into your Google, you will get very interesting paper. So we have taken this regularizer from there. Then we have put into here. Now you have the forward model as well as the regularizer. Now you can form this ADM equation. So three updated equation you can find out, because one regularizer you have, one forward model. Okay, so this is the updated equations. So now these are the performance matrices. So peak signal to noise ratio. So remember, you must know that when you have the reference images, so you have some type of measure performances to see the performance of that particular algorithm, like peak signal ratio, mean square error, structural similarity index, mean absolute error. So these are the performances when you know the ground truth image. And if you don't know the ground truth image, suppose in the practical case you don't know the ground truth image, so you can have some measure performance like equivalent number of looks, coefficient of variation, mean of ratio. So these three are without any ground truth image. So these are the two images we have taken. So we have compared this the regulation by denoising ADMM, BM3D. So here the BM3D acts as a, that the block matching 3D. So it is act as a denoiser. So we have seen the PSNR in this case is higher, as well as SSM and MAE also lower, and the time is also lower. So this is for another image. So in this case, okay, this results are better. Okay, in fact, this is also our paper, but that result is better than this there. But here the MAE is less and time is better. So this is about, now you will see the image wise. So you can see this image and our original image is given here. Okay, so it is somewhat better matching compared to all other. But here you can see LLR is also one of the better algorithm. But here, though you can see the brightness is more and some smoothness is also occurring. So that's why the results for this one is coming not good, but it is visually somewhat also good. So then it is called ratio images. So in case of ratio images happens, if your output results what you have got, suppose you have got the denoised image, and if you will take the noisy image divided by denoised image, then it should give me only noise. So this is your noise part. Now you see the ratio images in this. So in other cases, you can get some here some edges are there, but in this case, okay, so this result is somewhat close to our ratio noise, not uh, okay. You can also still remove some edges are here. So other case, that is the in this case what happens, in these two images are downloaded and the noise has been added by us, but next you have taken the practical images. To practical images, and you have taken small some parts here to show you. So you can see, so this is that part, the degraded image, and it is the output image. You can see this the picture, you can recognize here much better compared to others. And in this case, so you cannot use that SSIM PSNR because here no ground truth image is available. So you have to use your ENL, equivalent number of looks, coefficient variation. Okay. So this is the MOR and SSI. So in all the this is REDMM, ADMM beam theory is much better. Similarly, the other case, other image. So the conclusion is optimization belonging to class of augmented Lagrangians such as ADMM and its variants are helpful to handle inverse imaging tasks. ADMM has gained a lot of attention among researchers due to its ability to transform unconstant optimization in constant ones and solve them by using a series of small local subproblems. So main benefit of ADMM is this one. The problem is unconstant. Sometimes you'll get unconstant problem, but it's difficult to solve. But if now you transfer to an constant problem and solve using the sublocal problems. Okay, so this is the advantage of the ADMM. Owing to the modular structure of ADMM, it is simple to implement and also enable to plug in any off-the-shelf denoising algorithm. So you see that here the prior model here this prior. So this is, you need not to go for a define what is. So you can take any of the cell. Okay, like here you have your BM3D, but there are many of the cell denoisers are there. You can use the R regularizar. So you go to the one paper is available, research paper, that is a regulation by denoising. If you go through that paper, there are many denoisers are there which you can put a regularizer, and that regularizer can be used for many type of problems. So here you can take, we have taken only for the denoising purpose, and you can use it for deblurring, you can use for sharpening, so you can use for many type of other tasks. Currently, consensus ADMM and ADMM net have gained a lot of attention from researchers. So now you can see this ADMM net and consensus ADMM. So this is one type of distributed technique, because ADMM you can decompose the problems into different type of sub-problem. Each sub-problem you can assign to each node or each computer. They can solve them independently and can go for the distributed optimization technique. So another type of ADMM, variation of ADMM is also available, that is called ADMM net. This can be used for to remove multiplicity noise and involving linear models. Efficient algorithms can be developed for processing of multi-loop images. So remember, this is the SAR images what you have taken, that is only a single loop image. So you can go for the multi-loop image and can apply these algorithms. So these are the references. So these are many references are there. So some you can see orange color are there, which are very important references which we are used to implement this algorithm. So now at this end my presentation. So we can go for some questions. So the audience can put some question in the chat box.
Yes, the audience can type their questions on the chat box.
So, sir, what is the possible application? You see, this application we have used only for the denoising purpose. You can go for debugging purpose also. And many problems are okay. If you go for the ADMM, like machine learning algorithm nowadays are useful. Because people are using machine learning algorithms because they are the libraries are available. But for the ADMM algorithm, libraries are not available. You have to write it down in your course. Okay, but the popularity of machine like the machine learning algorithm, you can use the ADMM algorithm many places. Okay, you can go for the image resolution, you can go for the missing pixel of the images, you can go for the deep learning. So those type of many things are there. So please explain E by G algorithm. E by G algorithm. I do not understand what is E by G algorithm. Okay, so if you don't have strictly convex function, so if you don't have, you see, this ADMM does not need any strictly convex function. You need only convex function, but the dual ascent method need strictly convex function. But the ADMM requires the convexity. If you don't have the convex, like in one of the case what we have solved, after logarithmic is there, so okay, I'll go to. Okay, I'll tell this one later, this evolutionary algorithm. But let's take this strictly convex. Strictly convex required for the dual ascent. Strictly convexity does not require for the ADMM, but the convexity is required. If it is not convex, then you first transform the problem non-convex to convex. In this case, that logarithmic function was there along with the some square function, so they are non-convex in jointly. So we have to first transform them to convex. Then later on, we have taken the transformation. For example, we have taken log transformation. So later on, we will take the e to the power of those things to reverse. So have I answered Ayushi from Ayushi? Okay. Definitely, ADMM generally used for the parameter estimation. So there is no problem to get the parameter. ADMM can be used for parameter estimation. There is no problem at all. You see this evolution algorithm with guided mutation. Okay, I have worked in some long back, but I can say this evolution algorithms, they are the heuristic algorithms. To get the particular minimizer, it is a difficult, although you may get or may not get, but you cannot say that is a minimum point. Okay, that is the sum optimal point for the evolution algorithm. Today you will get the minimum point, but next day someone get the better algorithm, then you can get the better algorithm. But when you go for the mutation, what happens in the mutation? Something you have missed in the solution you can bring to the original solution in the mutation property. Okay, so if we put the mutation into the evolution algorithm, that will be better compared to the evolution algorithm without mutation. If we put the mutation, then some solutions which are missed in the algorithm, then you can bring into the solution. Is it true that one meta gives the solution, then other meta also give? Is it true that if one meta gives the solution, then other meta also give the? You see, meta heuristic algorithms always give the solution, no problem. But which is better? You cannot say that GA is better than PSO, PSO is better than GA, because there is no mathematics available behind that. Okay. So meta-heuristics are, you try the meta-heuristic in the complex problems, because where many maxima, minima are there, you go and try there. It will be always better to use the meta-heuristic problems where a number of maxima and minima are there. If the number of maxima and minima are only one, it is always better go for the your standard gradient descent algorithms. So you have talked about forward model problem, how it is different from a backward problem. If it is in the, they will ask choose this meta, then what are the answer? If it is into, you see, in case of a meta heuristic, there is no mathematical foundation for them. You cannot say which is better. If you see, today you will take the genetic algorithm, you have done with some variables, and take the PSO, you have done in some variables. Now you change the genetic, you have got, suppose the PSO is good. Now you change the variables of the genetic algorithm, you may get good solution. Okay, but what happens, sometimes some algorithms are faster, like PSO have some equations available. Okay, so you can get, okay, meta heuristic algorithm, if they choose this meta, you see, choosing of the meta heuristic algorithms will entirely depend on the problem. You cannot say which is better. I will use for this, or this is the best problem. Okay, you cannot say.
Yeah.
How to obtain dual optimal and primal optimal using CVX. You see, in the CVX itself, it's a convex optimization toolbox already available. So here primal dual, you just frame the problem, you put those, suppose ax is equal to b, what is the value of x? Now you put a and b and find out the value of x. So the primal dual solution, you have to find out the problem, you have to solve on your paper. Now after getting the equation, that equation you can put inside the CBX to get the solution. So optimal primal, there is nothing. What to answer if somebody asks why? What to answer if somebody asks why you choose this meta heuristic? You see, you see, meta heuristic will be you are choosing depending on the your problem complexity. For example, genetic algorithm and PSO. Then people search PSO because this is very simple and some equations are already available. It can run the faster compared to other. Hello, am I audible? Not audible. Someone is telling. Okay. What happens if the domain of function is not convex? You see, if the domain of function is, you see, two things: domain of function and function is convex. Domain is a convex set. If the domain is not a domain is not convex set, then the function is not a convex function. So you cannot apply this ADMM. Okay. So first you convert somehow. Somehow you have to convert this one. If you are not able to convert, or you are, that problem is not convertible, then you cannot apply these algorithms. These algorithms are for only convex, and there are many problems which can be converted to convex very easily. What happens to the domain? When you ask somebody, okay, you can interview us. You see, for the meta-heuristic solution, so your conventional Professor Jagannath Nanda, he has done a lot of on things meta-heuristic. Okay, he can answer much better than me. But you remember, for the meta-heuristic solution, no one is better than other until unless you have to find out something inside that. For example, as I have told, G and PSO. PSO have two equations, so you know something. A meta-heuristic solution, how to defend our meta-heuristic? You see, but which are black box? Heuristic is not a black box. You are using the black box. You can write yourself the problem. You see, today the deep learning, machine learning, they are black box because you are using the black box. You can write yourself. You have to understand inside that. What is happening? Nothing is a black box. We are using as a black box because we don't want to write the programs. And we are just taking because they already is available. Then you put the signal and get the output. You write the program. Who stops you? Nothing is a black box. We are using the black box. That's why you are telling black box. You see, this backward problem actually I have never tried, so I can't answer on that. Okay, in the forward model, because that model name is forward, that's why it is called forward model. So backward problem is I didn't understand, or I don't know this type of problems. You see, these heuristic models I have left a long back ago. So Professor Jagannath Nanda, you can answer some of the heuristic answers. Okay, I have long back ago. So remember, all of you, heuristic models are only applicable if the function, if the problem is very complex. Go for that one. Otherwise, if the function can be solved by gradient descent or some type of mathematical optimization technique, so it is no need to
Yes,
use at that time.
we will have the sessions on hyperheuristic as well as meta-heuristic. So we will answer all those queries there. So nothing to worry. So all your queries on hyperheuristic, meta-heuristics, all will be answered. Today we have sessions by Professor Kusumdeep also, and myself will be taking the third session. So we will be answering all your queries regarding those. So thank you, Dr. Ajit, for enlightening us with the Adam multiplier method. Yeah.
Actually, you are not audible, Professor Jagannath. So, if can you send me in WhatsApp one message so that I can out if it is over?
Yeah, it is over.
अभी छोड़ के अपने करके देखें.